So we have x1, x2, xn from IID random variable from some distribution with some probability function f theta x. If x is continuous, then it will be PDF. If it's a PDF density function. If x is discrete, then it will be PMF, probability mass functions. Now, and theta belongs to some parameter space, cap theta, and generally what happens that once we observe xi equal to small xi, the samples. So I runs from 1 to n. Then the likelihood function is defined as, in that setup, as L of theta equal to product of equal to 1 to n. So product we can write it because of the independence. Okay. F of xi theta. Okay. So this is my likelihood function typically. Now, what Neyman's factorization theorem tells us, Neyman's factorization theorem so this concept of likelihood function is now, I think, almost 100 years old. I think Fisher first introduced this concept in his 1921 paper. So it's almost now 100 years, or actually more than 100 years old now. So consider the likelihood function L theta. Consider the likelihood function L theta. We just defined it here. A real valued statistic, real valued statistic T of x tilde is sufficient for unknown parameter theta. Theta is unknown, and if and only if, it's both sides, remember that, if and only if the following factorization holds. The following factorization holds. Okay, so what is that factorization? It says L theta equal to, you can write it as G of T x tilde times H of x tilde. So if that holds, if you can do that, if you can write the L theta in this format, then you can say that T is sufficient statistic, where two functions, G, this is G of theta, and H are both non-negative, G depends on theta, and H is free of theta. H will be completely free of theta and G will completely dependent on theta. If that happens, then you can say T is sufficient statistic. So this is called Neyman's factorization theorem. Okay, so this entire thing I'm just putting into a box. This is typically called the Neyman's factorization theorem. Now, proof, I'm not going into the proof. The proof is somewhat in the same direction what we prove for what we discussed, what is the sufficiency theorems and all these things. So you can find the proof in two books. One in Mukhopadhyay's book, page 289. In Mukhopadhyay's book, it's page 289, and in Kasselberger, it is there in, let me see which page it is.
276.
276. In Kasseler and Barber. Who is it?
So, Orpon.
Oh, thanks, Orpon. Page 276. So I'm not going into the proof. Rather, we will discuss this theorem a little bit. If you look at this theorem carefully, it's sort of you will figure out, and if we do one or two problem, you will figure out that this factorization theorem is not actually to verify if a statistic is a sufficient. Rather, we can start with a likelihood function, and we can try to write this likelihood function into product of two functions, G and H. And if we can come up with a function G, which involves theta, and we can come up with a function H, which does not involve theta, but only function of X, then we can say that, okay, there will be some kind of statistics will be involved in the G part, and we can say that, okay, that statistic is sufficient statistics for unknown parameter theta. So let me do it for two problem, and before we, okay, let me do one problem and then I'll do another small theory. So if we do one example for binomial distribution, okay, so it will be quick, it will be a small binomial distribution, it will be a small problem, so it will be quick. So basically x1 x2 xn, let's consider, even take a simpler Bernoulli T. Okay, so what is the parameter space theta here? P is in 0 and 1. So my basically my parameter space is 0, 1, the range, the box 0, 1. And then my likelihood is LP product equal to 1 to n p to the power xi 1 minus p to the power 1 minus xi. So I can write this as p to the power summation xi 1 minus p to the power n minus summation xi 1 to n 1 to n. Now once you write it in this way, I can write this also, p to the power t 1 minus p to the power n minus t, where t equal to summation xi equal to 1 to n. Okay. Now, you see, can I write it in this way, where g p of t equal to times g of x tilde, where g p t is p to the power t 1 minus p to the power n minus t, okay, and h x tilde equal to 1 for all x tilde. Can I write it in this way? Anybody have any doubt? So hx equal to 1, I'm sort of saying it's in a trivial sense. So I'm just assuming, okay, here is a 1, okay, and I'm calling it, okay, hx tilde equal to 1 for all x. And then it nicely fit into the Neyman-Fisher factorization theorem. Hence, we can say that by Neyman-Fisher factorization theorem, Tx tilde equal to here summation xi equal to 1 to n is sufficient statistic. Correct? So similarly, we can show it for Poisson also. In the Poisson case, Poisson distribution case, what will happen? X1 to xn will follow, say, IID. Again, we are making our life simpler by making assumption of independence. Lambda is on the real line, positive side of the real line. So that is my parameter space. So I can write likelihood of the lambda as product 1 to n e to the power minus lambda to the power xi by xi factorial. And you can write it in that way, e to the power minus n lambda to the power summation xi divided by product I equal to 1 to n xi factorial. Now you see, I can write it as g lambda t hx tilde, where g lambda t is equal to e to the power minus n lambda to the power t, where t is summation xi. Okay, and h of x tilde, I can write it in this way. So this h of x tilde is completely free of lambda. So now again, I'm writing this thing as a function of two part, and so by Neyman's factorization theorem, T is sufficient stat for lambda. Now you see, we already proved on the day one this T is sufficient, but what we have not proved is if x bar, which is T by n, is sufficient. Correct? Are all of you with me?
Yes, sir.
So this is what we want to show. So a small result, if I just prove this result, that any one-to-one function of a sufficient statistic, function of a sufficient statistic is sufficient statistic. That is what we want to argue. Suppose T x tilde is sufficient statistic. Somehow we know, either by factorization theorem or by Fisher information's theorem that previously we showed, that somehow we figured out one sufficient statistic. And we define T star x tilde equal to R of T of x tilde for all x tilde, where R is a one-to-one function. With R inverse. Okay. Now I know T is suppose we can now consider the factorization theorem just we discussed. So the factorization theorem, by factorization theorem, L theta G of G theta of T H of x tilde, we can write this guy as G theta R inverse of T star of H x tilde. Since T star x is R of Tx, we know that. So I can write Tx as R inverse of T star x. I'm just using that. Now you define G star T as G of R inverse T. Then I can just simply write it as this L theta. You can write it as G star of T star Hx tilde. Hence, again by factorization theorem, again by factorization theorem, we can say T star is also sufficient. So that's all we need. So now by this result, we can say that for Poisson, X bar is also sufficient statistic for lambda. Similarly, you can show that X bar is also sufficient statistics for proportion when you are doing for binomial distribution or Bernoulli distribution. Okay. Now, what I'm going to do another example for two parameters. Okay. For normal with mu sigma square, well, both mu and sigma square are unknown. So suppose let us consider this example. Suppose x1, x2, xn, they're all IID, follow normal distribution with parameter mu and sigma square, where mu is in the real line and sigma is in the positive side of the real line. Okay. So my theta is a two-dimension theta, mu and sigma, mean and standard deviation. So my chi is in real line. So my x1, x2, xn, they belong to the sample space chi, which is basically real line. And my parameter space theta is effectively the products of this. So now we have to find a sufficient statistic for theta. We have to find, now remember that both mu sigma are unknown. So I need, when I'm saying, so my theta parameter is a two-dimension parameter space. So I need a parameter for estimator for mu. I need a statistic which will basically contain the information for both mu and sigma. So we have to find sufficient statistic, sufficient stat for theta equal to mu and sigma. So both mu and sigma. So again, what we will do, we will start with likelihood function. So what is the likelihood function on normal distribution? 1 by sigma square root 2 pi to the power n. And then I'm just taking the likelihood function from the book, but you can write the, actually you can write the, what you can do, this is the likelihood function. If you go up, so you can put the PDF of normal distribution and then do the little bit of algebraic manipulation, and you can come up with this form that I'm writing here. Summation xi square 1 to n minus 2 mu summation xi plus n mu square divided by sigma square. So this is the likelihood that you will find. Now what I'm going to do, I'm going to write this guy as T2 and this guy as T1. Okay. So I can write this as G theta of T1 and T2 as 1 by sigma to the power n exp minus half T2 T sub 2 minus 2 mu T sub 1 plus n mu square divided by sigma square, second bracket close. And h of x tilde is equal to 1 by 2 pi to the power n by 2 for all x tilde. Now clearly again we able to write this likelihood into two form, and we can say that okay, this T1, this T by factorization theorem, by factorization theorem, T equal to T1 comma T2, which is basically summation xi 1 to n and summation xi square from 1 to n. These two parameters, statistic is jointly sufficient. Jointly sufficient. Okay. Sufficient for theta, which is mu sigma square.
So in this case, our sufficient statistic is a vector.
Yes, absolutely right. So this is extremely important, and that is why I chose this example, that you have to understand that my sufficient statistic is not necessarily has to be a scalar quantity. Why? Because my parameter space itself is on the 2 dimension. So I need my sufficient statistic is also a 2 dimension object, or it's a vector. Now, one thing I can do again, that small result we can apply, that we can apply x bar is 1 by n summation xi, which is t1 by n, and s square is, we can define s square as 1 by n summation xi square minus x bar square. These are also one-to-one function of, so I can write it as a sort of a t2 by n minus t1 by n square. So this is also a one-to-one function. So I can say this t star, which is x bar comma s square, is also jointly sufficient statistic. Jointly sufficient statistic for theta. Okay. Acha. So I have a now. So can I say that is tx tilde equal to x tilde itself? Suppose I define that tx tilde is just x tilde itself. Can I say this is sufficient for theta?
Yes, sir. By factorization theorem, we can
Correct.
write the
Correct. By fact, you can put it into the factorization theorem and you can show yes, the sample space itself is sufficient. But the main problem is it's in the n dimension, and we want to. There is no dimension reduction in that sense. So yes, answer is yes. Okay. I think I would like to introduce one more small concept called minimal sufficient statistic. The definition of minimal sufficient statistic is Tx is minimal sufficient statistics. Tx is minimal sufficient statistic if for any other sufficient statistic, other sufficient statistic t say dash x. So tx is also sufficient statistics. T dash s is also sufficient statistics. Tx is some function of t dash x. Okay. So it's like I'm saying, so the purpose of minimal sufficient statistic is somewhat is this, that I know that tx tilde equal to x tilde is sufficient statistic. In some way, if I can just define a t dash x tilde, which is a one-to-one function, somewhat one-to-one function of tx tilde, which is a sufficient statistic, then it will contain effectively all the information. So if say summation xi is sufficient, then you can say x bar is summation xi by n is also sufficient, and hence it is minimal sufficient statistic. But at this moment, I want to introduce a very important concept, something called ancillary statistics. That very cool concept. In a sense, it's actually a perpendicular opposite concept to sufficient statistic. So sufficient statistic contain all information about theta that is available in the sample. But ancillary statistic is a statistics which does not contain any information about theta. You can also have a statistic which does not contain any information about the theta. And such a statistic called ancillary statistic. Okay, so let me give an example. So let me first write down the definition. 282 Burger. So statistics is of x tilde whose distribution, basically it means whose sampling distribution, whose distribution, if x tilde is a random variable, then s of x tilde will be also random variable and it will have its own distribution, but its distribution does not depend on theta, is called ancillary statistics. So what does it actually mean, that why we need to understand ancillary statistics? Let me give you an example and then it will be easy for you to understand. So say x1 to xn follow, say IIT normal mu sigma square. We know T summation xi comma summation xi square, they are jointly sufficient. Jointly sufficient. Okay. Now, I want to understand, we do know some sense that T dash itself is x bar and s square. And X bar generally estimate are used for the mu, and A square estimate the sigma square. Now my question is, does X bar contain any information about sigma square? Do you understand what I mean?
It contains information about mu, but I don't know
Correct.
about sigma square.
Correct. Because one thing we do know, expectation of X bar is mu. What about variance of X bar? Sigma square by
N.
n. What is the distribution of X bar? Can you figure it out?
Normal
mu comma
mu
sigma by
comma sigma.
Correct. Normal with mean mu and variance sigma square by n. Is the proof being done in the class, or it is being said just?
We didn't prove it, but it was said in the class.
It was said in the class. Okay. Did RVR done the moment generating function in the class? Not really.
He gave an introduction on moment generating functions.
yes,
Okay.
he did it, but I think a revision would be better of it. I mean, a slide digression.
Okay. So I'll do it later, because that will be a digression from the topic. Okay. So I'll do it later. Keep me reminded, maybe. Well, let us first finish this topic. We are almost done with this thing. So one thing we are seeing that the X bar, the distribution of X bar depend on sigma square. Okay. You see, and variance of X bar. Now next level of question is, my next question is, does S square contain any information about mu? We do know it does contain some information about sigma square. So let me take this definition of A square. A square is 1 by n minus 1 summation I equal to 1 to n xi minus x bar whole square. Okay. Now one can show that n minus 1 by times A square divided by sigma square. If this distribution, this follow chi-square distribution with n minus 1 degrees of freedom. Okay. So that means expected value of n minus 1 times a square by sigma square, the expected value of a chi-square distribution is degrees of freedom. So n minus 1. Now n minus 1 by sigma square, it will behave as a constant. So I can take this out. I can take this out and do the adjustment. So I can show expected value of S square is sigma square. What is the variance of S square? Can anybody tell me what will be the variance of S square? See, n minus 1 times S squared by sigma squared. This guy follow chi square n minus 1. So if say y follow chi square with some new degrees of freedom, then expectation of y is new and variance of y is 2 times new. Correct? Yeah. So this is a result we are going to use. If we are going to use this result, okay, then what we will do? 2 into n minus 1. Now n minus 1 times s divided by sigma square. This we will treat it as a constant. We will take it out, but when I'm taking a constant out of the variance, it will be squared. So it will be n minus 1 square divided by sigma to the power 4 times variance of s square 2 into n minus 1. So I can write this as variance of s square as 2 sigma to the power 4 n minus 1. Correct? So my s square, so basically what are the properties we got? We say that, okay, n minus 1 s square by sigma square follow chi-square distribution with n minus 1 degrees of freedom. This is equivalent to say my s square follow sigma square times sigma square by n minus 1 times chi-square. So it is a scaled chi-square distribution with n minus 1 degrees of freedom. So it does not involve, the distribution does not involve any mu. My expectation of s square is sigma square and variance of s square is 2 sigma to the power 4 by n minus 1. So s square, the distribution of s square does not involve mu at all. The distribution of s square does not involve mu at all. So though you see that x bar do have some information about sigma square, but s square is completely free from mu. S square is only containing information about sigma square. So s square does not contain any information about mu. So s square is an ancillary statistic for mu. So you cannot, if you want to estimate or if you want to do some kind of analysis with for mu, you cannot use s square. S square is not going to help anything. It doesn't contain any information about s square mu. So S is an ancillary statistic. So it's kind of complementary to opposite. Finally, I will talk about another last example, and this is, I found, a very intriguing example indeed. This is the example from Mukhopadhyay, page 312. Example from Mukhopadhyay, page 312. Example. So this is by D. Basu. Professor D. Basu was professor at ISI Kolkata. He was a C.R. Rao student, but he passed away little early. So the example that he came up with was pretty intriguing. So suppose X and Y, they are bivariate, they follow bivariate normal 0, 0, 1, 1 row. Okay. So it's like you have two variable X and Y. This is 0 here, 0 here. So if this is X, this is Y. This is the marginal distribution of X, which is between, say, minus 2 and 2. Here it could be minus 2, here is 2, this might be minus 1, here is 1. Similarly, you got a sort of a minus 2, minus 1, 0, 1, 2. Okay. So what it says that, and you know that X, mean of the X is somewhere 0. You know that. Its deviation is 1. Similarly, Y mean is also 0, and its deviation is 1. So that means, so technically there are 5 parameters: mu for X, mu for Y, sigma for X, sigma for Y, and the rho is the correlation coefficient. Okay. What we found, now if you look into the, so now I can say that, okay, T1 is my X and T2 is my Y. So my T is basically T1 comma T2. I can say that T is sufficient statistic for rho. So only parameter I have in this distribution is rho. Remember that. I know what is the value of exact value of mu X. I know what is the exact value of mu Y. I know exact value of sigma X. I know exact value of sigma Y. What I don't know, what is the correlation. Now T is sufficient statistic. T is sufficient statistic for rho. Can you argue that? This is the exact same argument that if I have Tx equal to x tilde, then x tilde is sufficient. All I have an x and y, one observation. That's all I have. So jointly this xy will be sufficient for rho. Are you with me? Okay.
Yes, sir.
Now look into the distribution of T1. If the marginal distribution only follow normal, univariate normal with mean 0, standard deviation 1. Marginal distribution of T2 only follow normal, univariate normal with this one, right? 0 and 1. Any of them involve rho? The answer is no. So that means T1 and T2 separately, they do not contain any information about rho. But jointly, they do contain all the information about rho. You understand? So that means T1 is ancillary for rho. T2 is also ancillary statistics for rho, but jointly they are sufficient for rho. This is one of a very cute corner problem of mathematical statistics, but it brings a very, very crucial understanding about the rho. And I'll tell you that before, but up to this, are you guys with me or not? Are you guys with me?
Yes, sir.
Okay. Now what it tells us that X, they separately you cannot say anything about rho. Jointly you can say everything. Suppose, and actually it has happened with me, the actual data was, I think X was birth weight of some children and Y was birth weight of some other children. So what happened in the same health center, so baby was so new baby was born, and they were keeping the birth weight and birth weight and I think birth height. Sorry about that. Birth height. Correct. Birth height of some other children. The only difference was that I think this was in some months, and the X was collected in some months and Y was collected in adjacent month, and they believed that okay, they are somewhat similar, the population was somewhat similar, and they wanted to estimate the rho. It's like I have now situation was I have some points on X, but I do not have corresponding Y here. So I cannot plot this point on the scatter plot. It is only on the X-axis. I have another point on X, but I do not have corresponding Y here. So I can only plot it on the X-axis. Similarly, so all these points are on X-axis because all these points corresponding Y was not recorded. Similarly, birth height was recorded, but corresponding X was not recorded. So I have the marginal distribution of Y, I have the marginal distribution of the X, but I cannot compute correlation. I will not be just having this information. I will not be able to calculate or even rediscover or whatever, rescue row. Because if I know this x value and corresponding y value here, then only I can plot it here. Similarly, I can, for this point, if I know whatever that point here, I can plot here. And this way, if I just plot all the points, that means for each observation, I need xi and yi together. If I have them together, I can compute the row. But separately, I will not be able to, calculate the row or calculate the correlation. Okay, guys?
So
Mm-hmm.
over here, the example you gave, it's quite clear because it's like two different data of two different groups of children are used. So
Correct.
we cannot really, find any kind of association among two different observations. So,
Correct.
but where is it useful? Because this right now appears very intuitive. I mean,
I
are
mean,
there
that is
scenarios where
what.
it would get misleading for us to consider that it would be a sufficient statistic?
No, I'm not saying it will be a sufficient statistic. I'm not saying that. But what I'm trying to say that if you have to be, again, I mean, what is the answer? So that means if what I'm trying to say that jointly x and y may contain some information here. In this case, they will contain some information about rho. So that means if I have data like this, x1, y1, x2, y2. So this is a first observation for which both x and y I know. x3, y3. In this way, I know that they have some information about rho. I will know that. So suppose for some example, I'm just assuming this, even if I just say 0, 0, 1, 1 row. For simplicity, they're scaled already. At least I do know that these data has some information about rho. But if you have, say, x1 to xn and y1 to yn, I do know that they separately follow normal 0, 1, normal 0, 1. But unless I can pair them, I will not be able to say anything about rho. That's all I'm trying to say.
Oh, okay. Yeah.
So in order to preserve the geometric structure, you have to have the paired information. As soon as you're losing the geometric structure, so rho is actually is a parameter which tells us about the geometric behavior of these point clouds.
Yes, sir.
So that is what I am just trying to make that point. Okay. There is it is 1:10 almost. One last topic probably we would like to touch is complex statistics, but unfortunately, complex statistics. Okay, I'll do it next week. I think. And then with that, I think we will finish this chapter. I think majority of the problems, I think the topic will be covered, and then I will assign some assign some assignment, and whoever can do that, that will be good. So like small topic we are left with is complete statistic. We'll do that and then we are done for this chapter, and then we'll move on to next chapter, point estimation. Okay. All right, guys.
Thank you, sir.
Mm-hmm.
I said thank you, sir. That's it.
Thank you. Yeah. So see you on Tuesday before attending the visualization course. Have a nice weekend.